Welcome to week 3. We're going to be talking about electrons this week. Now, with electrons, we know that electrons go around the nucleus. So why aren't they pulled into the nucleus and held there? Niels Bohr proposed that electrons must have enough energy to keep them in constant motion around the nucleus and compared the motions of electrons to motions of the planets. So he thought that yes, there's a nucleus with the protons and the neutrons here. And then we have orbits, just like the planets. However, he said, unlike the planets, the electrons occupied orbits of only certain amounts of energy. So this would be energy level 1 and energy level 2 and energy level 3. He said that one way to increase energy of an electron is to supply energy in the form of high voltage electricity. The other is to supply electromagnetic radiation or radiant energy. There's actually several different types of electromagnetic radiation known as the electromagnetic spectrum. Now, radiant energy will travel in forms of waves at the speed of light, which is 3 times 10 to the 6 meters per second. Waves can transfer energy. So if you have those glow-in-the-dark stars, you can actually leave them out and the sunlight will charge them because those waves are carrying energy. You use your microwave because those microwaves carry energy. The microwave actually is called that because of the microwaves that they supply. Electromagnetic radiation includes radio waves, microwave radiation, radiant heat in a toaster, and visible light, just to name a few. The electromagnetic spectrum is the whole range of electromagnetic radiation. So here you have the whole spectrum. You have radio waves, microwaves, infrared rays. That's your IR rays. Visible light is even part of the electromagnetic spectrum. Ultraviolet light, X-rays, and gamma rays. Notice the size of the wavelengths. Gamma rays are really tiny. 10 to the negative 12th is the size of their wavelength. That's 1/1,000,000,000th of a meter. That's how tiny they are. Whereas radio waves are 1,000 meters or more long. So you can see they have a wide range. The smaller the wavelength, the more energy it has. And therefore, the more dangerous it is. The larger it is, the less energy it has, and the less dangerous it is. So we know that energy of motion of the electron and the energy of light produce the electromagnetic spectrum. And scientists passed a high voltage electric current through hydrogen just to see what would happen. And hydrogen absorbed energy and returned the energy in the form of light. They were really intrigued by this. And this was one of the experiments that they did with Niels Bohr, and why he said, well, they're in energy levels because you pass the high voltage electric current through hydrogen, that electron will absorb that energy and go up to the next energy level. And as it's releasing that energy, it's going to be in the form of light. That's what happens with your glow-in-the-dark stars. You excite all of your electrons, and as they come back down to ground state, that's where they were initially, it's called ground state. They come back down to ground state, release that energy, and you see it as light. Now, they took the light that hydrogen emitted and they passed it through a prism, and it showed only a few specific frequencies. So here's hydrogen that they excited and then let it cool down. And as it cooled, the light was emitted, and they put a prism next to that light, and they noticed they had violet, they had blue, they had like a turquoise, and they had orange. They did it to helium too, and they noticed that helium had even more colors and more lines than hydrogen did. What you just saw is called an emission spectrum. That's the spectrum of light that's released from excited atoms of an element. And they actually use these emission spectrums to determine what elements are present in other planets, which is kind of neat that they can do that to determine, oh, look, there's oxygen on that planet, or that planet is mainly carbon dioxide. Just based on the emission spectrums that they've collected, they can use those to match up and identify what elements and compounds are present. Now, as you looked at that, you saw that hydrogen had 4 lines, but helium had more. It had 6. Why? Bohr theorized, remember, we're just coming up with theories, and then we experiment some more. We adjust our hypothesis, we experiment some more, trying to figure out what is happening. Right now, they're trying to determine how electrons are staged in the atom, what their structure is. Bohr theorized that electrons absorbed energy and then they moved to the higher energy states. So the excited electrons gave off that energy as light waves when they fell back to a lower energy state. He said that electrons can only have certain amounts of energy. When they absorb energy, electrons absorb only enough to move to a specific higher energy state. When they fall back to a lower energy state, they emit only a certain amount of energy, the amount of energy that they initially absorbed, which corresponds to specific colors. So because electrons can have only certain amounts of energy, then they can move around the nucleus only at distances that correspond to the energy amounts. That's why he thought it was like an orbiting planet. It's stuck in that orbit. So he said there are energy levels, the regions of space in which electrons can move about the nucleus of an atom. Now he was correct about there being energy levels. We know that there are 7 different energy levels from looking at the periodic table and how it's arranged. And we verified that through multiple tests. But he was not correct in that they had a planetary motion and just stayed right there in orbit like the planets around the sun. More tests were done, and they realized that energy levels are spherical regions of space around the nucleus in which the electrons are most likely to be found. And they take up little space, but they move so rapidly through the space surrounding the nucleus. And that it isn't just in orbital fashion, it could be that whole spherical region around the nucleus. So the space around the nucleus of an atom, where the atom's electrons are found, is called the electron cloud. Because remember, they're moving so rapidly that if we could take a snapshot of it, you would just see like a little blur like this from the electron moving so quickly. And it looks more like a cloud. There's a high probability of finding the electron in that space, but it's extremely difficult to pinpoint it. You can't pinpoint both its speed and its location at the same time. You can pinpoint the speed, but if you have the speed, you can't pinpoint its location, or you can pinpoint its location, but not its speed. It's kind of difficult. So here is what it looks like. You have the electron cloud. The darker area is where the electron is most likely to be found. The lighter area here is still probability, but not as high probability of finding the electron there. And then, of course, this is your nucleus. This is a helium atom. Now, each energy level can hold a limited number of electrons. The lowest energy level is the smallest and closest to the nucleus. It can hold a maximum of 2 electrons. The second lowest energy level is larger because it's farther away, and it can hold up to 8 electrons. The third energy level can hold up to 18 electrons. Now, valence electrons, these are the electrons in the outermost energy levels. And these are what are involved in bonding with other atoms and give the characteristics to the chemical characteristics and properties to the atoms. Now, valence electrons correspond to group numbers. So all atoms in group 1 have 1 valence electron. All atoms in group 2 have 2 valence electrons. Groups 13 and 18, you kind of drop the 1 in front. So group 13 has 3 valence electrons, 14 4, 15 5, 16 6, 17 7, and 18 8. Those groups are the only ones that you can predict their valence electrons. Transition metals, the lanthanides, and the actinide series, they are more complex. So you cannot predict the amount of valence electrons in the transition metals and the lanthanide and actinide series. You can only do it for the main group elements, groups 1, 2, and 13 through 18. Now remember, it's the valence electrons that interact with electrons of other atoms. And many of the chemical and physical properties of an element are directly related to the number and the arrangement of valence electrons. We're going to stop there for now, and I'll see you next class.